Hi everyone, welcome to the Opamp Masterclass video series. In the last videos, we had seen open loop configurations. In this video, we will be watching and we will be understanding what is closed loop configurations and why it is needed. It is also called as the closed loop amplifier. It is also called as voltage series feedback amplifier. Whatever the name is, let us go and understand how the feedback mechanism works on the amplifiers. Let us consider open loop configurations. You can see here, this is a non-inverting terminal. This is inverting terminal, and this is output voltage V0. This is input terminal. This is V2 input terminal. We can start the deducing the equations with the open loop configurations assumptions. And so later we can deduce the equations for the closed loop amplifier. What is open loop and what is closed loop? I'll try to reiterate once again. Open loop means the output voltage or a small portion of the output voltage is not fed back to the input system here. So it is called as open loop configuration. If I try to put a small portion of the voltage V0 back to the input, I connect through this V output voltage to the back to the input through what is called as the few passive circuits, and this is called as few closed loop configuration because we're taking the small portion of it and we are connecting back. The earlier one, the one which I just now said it, the one which actually you give the feedback with the feedback resistor, we can call it as a positive feedback. And it's the same thing which actually provided to the what is called as to the inverting terminal, it's called negative feedback circuits. We have a different applications for the op-amp where we use the positive feedback and where we use the negative feedback. We are going to study the non-inverting amplifier with this closed loop configuration. Now, let us go with this word non-inverting amplifier. Let us draw a non-inverting amplifier. That means you have a input which is connected to the V1 terminal, and since it is with feedback, I cannot leave it blank open. I have to tap from the output. I cannot simply tap the output. I want to using a resistor network so that I'll get some voltage drop across the resistor network. For all the people who are in the initial engineering semesters, you can see that the voltage across this particular resistors is with respect to the ground. The voltage across this terminal is with respect to the ground. The voltage across this resistor is again with respect to the ground. Voltages are measured with respect to the ground. For simplicity, I call R1, and this is called RF. This is V out. You can see small portion of the output voltage feeding back to the by using the resistor divider network. There is certain drop here. So the drop across here, I don't know, something X drop, and here it is Y drop. I don't know what the Y drop is, but certain drop of the voltage is fed back into this V2 terminal. Now, I call this drop as VF for simplicity. Now, let us start understanding what is a closed loop configuration. I'll give you an analogy. There is a horse which is running at a very, very high speed. If you want to control the speed of the horse, then you have to control the reins. Reins are nothing but your leather belts, which is tied. A rider has to control that. So, based on the speed, he holds the reins and he tries to control the speed of the horse. A similar way, op amp, by its nature, it has a very, very high gain. You don't want such a very high gain because you need an intended gain for a intended applications. For specific application, gains are calculated and we want those intended gain. The reason is that the circuit has to actually behave as expected. It has to be stable. I hope you understand this analogy. Let us try to understand gain of the non-inverting amplifier. So what is the gain of the non-inverting amplifier? Because we have given already the closed loop now. First to start with, what is closed loop gain? It is nothing but output by input. Output is out V naught, input is V in. Let us keep this value. This is the intended gain that we are trying to find out from this particular configuration, right? How do you get the gain? I told you, you're going to get the gain based on the feedback circuit only. This is the intended gain. This is like a rain. This is like your leather belts. You're using a small portion of the V naught based on the ratios of the R1 and RF. Fine. Now, anything in the amplifier, op-amp amplifier, we have to start with the open loop assumptions, open loop configuration assumption. What is the output voltage? Output voltage is nothing but the open loop gain V in multiplied by it is V1 minus V2. It is nothing but nothing but the difference of the this voltage V1 minus V2 into gain is nothing but V naught. You can go check out that open loop configuration in my previous videos. Now, what is V1? Is V in. What is V2? It is the voltage at this particular terminal is measured with respect to the ground is nothing but your this VF. Whether this point is here or here, it is one and the same. The voltage V2 measured with respect to the ground is nothing but the same voltage we are seeing here. That is VF. So this is the point which has been tied here. It is just a simple connection. This voltage VF appears at V2. What is VF? Use the voltage divider rule. Go check out in my previous videos about the voltage divider rule. It is a small portion of the V naught falling across or dropping across RF counted across the total resistors. Okay, this is equation 1. Now we know what is VF, right? We know what is V1. We know what is VF. This is VF. VF is equal to V naught into RF divided by R1 plus RF. We have all the values of the V1, V2, and we can substitute to the equation 1. Output voltage is equal to A into V in minus what is V2? V2 is VF. VF is here. Which is nothing but equal to A into V in minus A into V naught into RF divided by it is R1 plus RF. I'll simplify this. How do I simplify it? V naught plus AV naught RF divided by it is R1 plus it is RF is equal to A into V in. V naught is equal to 1 plus here. Let us simplify this one. Just keep watching that V naught now. It is A into V in into R1 plus RF. It is R1 plus RF plus ARF. Now, we have to make certain assumptions. Now, you have the V in here. Bring that V naught divided by V in, which is equal to A. It is R1 plus RF divided by. Now, can I write the same thing? A is what in terms of thousands and thousands. This is a very, very huge value multiplied with another resistor is a huge value. This is a very, very small value. I can just write it as A into RF. I don't want this is negligible actually. So A and A is cancelled and the output voltage divided by V in is nothing but the intended closed loop configuration is can you simplify this one? It's 1 plus it is R1 divided by this is RF. This is what we wanted. Again, I'm going to write this one. It is AF is equal to it is 1 plus R1 divided by RF. If you have this equation, you can design a closed loop configuration with an intended gain. You can check the R1, you can check the RF, and you can get an intended gain here. This is what we wanted to actually derive from the non-inverting amplifier with closed loop configuration. Now, I will show you very simple methodology how you can arrive at this particular formula very quickly. Let us write the non-inverting amplifier with feedback very quickly. There is a connection. This is V in connected to ground, and this is V naught or V output. This is V1 and this is V2. The output, as we told, this will be two resistors. It is R1 and this is feedback resistor. It is RF. Disconnected. This is connected to ground. What is this? This is feedback. Instead of deducing such a long formula, this is very simple one. If you know the ideal op-amp equations. What is the ideal op-amp equation? It is first let us understand what is the gain of an op-amp amplifier. What is the gain of this op-amp amplifier? It is first let us see that what is the difference is that VD. The gain is nothing but equal to A is equal to output is nothing but equal to V out divided by VD. So this is nothing but output by input, that is the gain. Suppose if you have 100 rupees and input is only 5, 20 is your gain. You can think of that way, okay? Output by input. Now, what is VD? VD is equal to, it is V1 minus V2. This is in the non-inverting terminal. This is in the inverting terminal. It is V1 minus V2. I will rearrange this one. It is VD is equal to output voltage divided by A. So what is A? A is gain. We all know that in the ideal op-amp equations, what is ideal op-amp equation? The gain is huge, very, very, very huge. As it tries to go towards a very high gain, towards infinity, the whole thing will become zero equations. So VD is equal to zero. What is VD? At this juncture, VD is nothing but minus V minus V1 minus V2. So that means this will approximate V1 approximately equal to V2. The non-inverting terminal will try to equal this particular voltage, that is V2 terminal voltage. V1 becomes equal to V2 when there is a super high gain or its high gain. So with this assumption, what we can understand here is that V1 is equal to V2, right? What is V1? V1 is nothing but equal to your V in. What is V2? It is VF. We know in the last a few minutes ago, we saw that what is VF? It is the voltage divider formula you have to apply here. So VF is nothing but equal to, it is the portion of the V naught I'm trying to tap from here, which is found across RF with respect to the total resistance. Okay, so now output voltage, okay, is equal to, you can send this one here, V in into it is R1 plus RF divided by it is RF. So output voltage divided by input voltage, which is nothing but output voltage divided by the input voltage. Now it is not an open loop gain, it is nothing but a closed loop gain. It's AF. It is nothing but equal to, let us rearrange this one. It is 1 plus, it is R1 plus RF. The same formula we got it earlier. So this proves that, so when you have the ideal op-amp equations very clear, you can arrive at the op-amp design equations very easily. So first go and watch my ideal characteristics of the op-amp very carefully, twice, thrice, until you get hold of the initial yeah, or the ideal equations. Now let us design the non-inverting amplifier. Output voltage V0, V1 terminal, V2 terminal, and here what we are trying to do, we're going with the feedback circuitry, and we are trying to convert a non-inverting amplifier. So I think if you just look at my videos few minutes earlier, few minutes before, this is the circuitry, a voltage divider circuitry to feed back into the V2 terminal. This is how it has been shown. And now it is normally, we will tell actually why the R1 is needed and all those things later. So just now, just follow this particular one. This is always with respect to the ground, right? Now, this is the output voltage here, V1 and V2 terminals. Let us understand now, we want to design this particular one. There should be some kind of a input data. Let us say V in is 10 millivolt. Fine. And V naught is, I don't know, what is R2? I don't know RF. What should be the V naught? Either you should know what is the gain, closed loop gain, or you should know kind of why it is a closed loop gain now. Because now we have connected back to this through the network. Either we should know what should be the output value for my applications, or I should know the gain, how much this particular, op amp we have it, and later we can adjust the R2 and RF. Now for simplicity, let us understand that my V naught should be is equal to 1 volt. From 10 millivolt to the 1 volt actually should amplify. Now, with this assumption, let us understand few basic ideal characteristics. What is input bias current? Ideally, it should be zero. But actually, in practical op-amp circuits, there will be little current which goes through the terminal. The same IB current which goes in here as well. It is the same IB, right? Now, if we just look at it, let us try to understand where is this IB is coming from. It is taken from this particular circuitry. Okay, let us, the current through this network output circuit is R2 and RF. This is the current which goes through R2 and RF, that is I2. Small portion of the I2 has to go into the IB. That means I2 should be bigger than IB, because if you have money, so that you can lend money to others. So I2 should be more. So let us let deduce some formulas here. IB, you can get it from the data sheet. You can see here, what is that? 500 nano amperes. I2, you can assume that, as I told you, this should be more, let us say 100 times then of the IB, which is 500 nanoamps. This is nothing but equal to 50 microamperes. What is I2? 50 microamperes. Okay. IB we know V in we know. And now what is to be understand here is that let us deduce some formulas to identify the R2 and RF. If we just look at this particular picture, this particular voltage, the voltage across RF that is being fed into the V2. Okay. If you remember, if the gain of the op-amp is very, very high, if the gain of the op-amp is very, very high, the voltage at the terminal V1 appears at V2. That means it equals. We can say that both the voltages equals. How, you may ask me? What is the closed loop, open loop gain? Open loop gain is nothing but equal to, it is output voltage divided by the VD. Okay. VD is equal to output voltage divided by AOL. What is VD? It is V1 minus V2. What is VD? This is the voltage, that is the V1 minus V2, which is nothing but equal to V0 divided by AOL. If the gain is very, very high, it goes to infinity, let us say that, then this particular portion will become 0, anything divided by infinity. So V1 minus V2 is equal to 0, or V1 is approximately equal to V2. That means as and when the gain is very high, the terminal voltage at the V1 appears at V2 itself, or the V1 and V2 both are equal. So instead of feedback voltage, can I call this as V in? So what is V in? V in is nothing but equal to, this is the voltage. You can identify this voltage using voltage divider rule. The voltage V1 is nothing but small portion of the V0 appearing across the feedback resistor RF measured with the total resistance R2 plus the RF. V in, V0, you know, what is V in and V0? So before that, just keep this formula. What is the current in this particular circuit? Is I2. So it is V in is equal to RF into I2, right? Or RF is equal to, what is V in? It is 10 millivolt divided by 50 microamps is nothing but how much? It's 0.2 into 10 to the power of plus 3, which is nothing but equal to 200 ohms. Here, you can always give 200 ohms. RF, you got to know 200 ohms. V in, you know, V not, you know, RF, you know. Can we deduce this R2 plus RF? Yes, that is easy. R2 plus RF is equal to output by input, right, into RF. So let me get this one first. I'll write it here. R2, R2 is nothing but equal to output voltage divided by input voltage into RF. You're bringing this side minus RF. What is output voltage? 1 volt. What is the input voltage? 10 millivolt. What is RF now? 200 ohms minus 200. 1 divided by, this is nothing but here, 0.1 into 10 to the power of 3 into 200 minus 200. Once again, it's 20 into 10 to the power of 3 minus 200, which is nothing but equal to 21 to 3 minus 200. So 21 to 3, 200 is nothing but 0089. So it is 19.8 K here. So you got it 19.8 K, 200 ohms. What is R1? What should be R1? R1 is very interesting. How you want to select R1? I want my impedances here, which appears between these terminals, should look alike. I should not have the varied input resistances. So, sorry. Now, in order to make that one now, what is the resistance if you just look at it because of this combination? It is absolutely nothing but the parallel combination of this R2 and as well as the RF. Okay, so probably I'm going to write somewhere here. It is R1 is equal to, it is R2 parallel RF. So what is R2? 19.8K parallel with 200 ohms. So now you can approximate that, approximate 200 ohms. So it is 200 ohms. So this can be 200 ohms. You got it now. This is the non-inverting amplifier with feedback circuit. Hope you like this video. Please give a thumbs up. Please do like this video. So it encourages me to bring some more videos as well. Thank you so much for watching.